Okay, now let us consider the example to understand the case 1 better. Case 1 that I have given a diagram, insertion happens to left of the AVL tree. In such situations, the solution is that you apply right rotation. Okay, so here it is, I have copied. If this is the case, this is the rotation solution. So now let us take this example. This is an AVL tree. Why? Because it satisfies the BST property. Also, it maintains the property of a balance factor. Now, quickly calculate the balance factor for each node. Note down for each node, each leaf node, the balance factor is 0. And then go to this node, the balance factor for this is 0, and for this is 1, and for this is 0, and for this is 1. Okay. Now it satisfies the balance factor as well as the binary search tree property. This tree is said to be an AVL tree. Okay. Now note down, the balance factor get affected whenever a new node is going to insert, or whenever we try to insert a new node in this AVL tree, or whenever we are trying to delete a node from an AVL tree. Now let us consider the case that I want to insert a node whose value is 2. Okay, and then see how the balance factor is get affected, and then this is the solution. Now for simplicity, let us take the case 1. Case 1 says that insertion happens to the left of left subtree of the AVL tree. Now you see this 2, since 2 is lesser than 8, we have moved to the left of 8. Since 2 is lesser than 6, we have moved to the left of 6, and it is lesser than 4, we have moved to the left of this, and this is the right place so that we can insert a new node. Okay, let us that new node is marked by this value. Okay, now because this new node is inserted, there may be a violation happens in the balance factor. Now let us calculate the new balance factor. For this node is 0, and for this node, earlier it was 0, now this is 1, now this is 1. Now the balance factor for the node 6 is 2, and now the balance factor for the node 8 is 2. Now you note down, as we already discussed, that in which of the path the new node gets inserted, only that path the balance factor gets affected. There is no balance factor changes in the right subtree, because the insertion was happened only to the left and left side of the AVL tree. Now this is the case satisfied. A new node was inserted to the left of left. Okay, so this is left. Okay, left of P. Now let me give quick decision to decide what is the node P and what is the node A. Okay, now you see this example. After insertion, you look at from the bottom to top, and then the very first node from the bottom to top whose balance factor is violating, that node is P. Okay, now this is the nodes whose balance factor is satisfied, this also satisfied, this also satisfied, but this is the node whose balance factor gets violated. Now the balance factor for this is 2, now this is P. Okay, now to the left of P, is A. So once we correctly figure what is P and then A, now the rest of the rotation method becomes so easy. Now let me repeat again, because students do a common mistake in figuring out the node P and then A. Now after an insertion happens, look at the BST from the bottom to top, and then try to fix the node whose balance factor is get affected, means whose balance factor is not either 0, 1 or -1, let's say 2, right? So that is the node P, and to the left of P is now A. Now you see this, the insertion was happened to the left of this P. Okay, left of this P and then A. Okay, this satisfies the case 1 and the insertion happens to the left subtree and its left subtree is 3 and then its left is 2. Okay, since it satisfies the case 1, we have to rotate this tree as I have discussed earlier. So what's the solution? You rotate this P to the right side once. That is also called a single rotation. Fine. Now let me give the solution for this. Okay, after a new node insertion 2, the balance factor of this AVL tree is affected and we are trying to make the tree balanced by rotating this node. Okay, now what is P here? P is nothing but 6 and then A is nothing but 4. Now you make A. So now A is nothing but 4. Okay, note down A's left child remains as such. So 3 followed by 2. And now this is the new node that inserted right now. No change because AL, no change. Now where does that P goes? P goes to the right of A. So what is P here? P is 6. So P goes to the right of 4 which is 6 and then no change in the PR because PR should be larger than P, right? So it should go to the right position. Now where that AR we have to move. What is AR? AR is nothing but node 5 here. That should go to left of P. Okay. So P is now 6. Now you see this matches. Okay. So now earlier this was P A. Okay. Now where we apply the rotation? We have applied the rotation here which is in the right direction. After we rotate this P, the P has to go to the right side of 4. Okay. So after rotation, P has come to the right side of A and then it satisfies. This is PR, this is AL and this whole this is AR. Now there is no change in this remaining portion. Now simply we can make that as such 9 and then 11. So no changes. No changes in the node 8 also. Now you see the tree is balanced right now. Okay. Now let us give the balance factor. All these leaf node is 0 and this also 0 and for this also 0 and for this is 1 and for this also 0 and for this 1, 2, 3, 3 minus 2 which is 1. Now you see for every node in this tree satisfies the balance factor. Also it is a binary search tree. Now what is the case? Now let me quickly recall the case 1 once again. When the new node happened to the left of A, P and then A, you apply the right rotation. After applying the right rotation, this is the tree and now this tree satisfies the balance factor as well as an AVL tree. Okay, this is about case 1. Next we will discuss case 2.